In a previous class, we will discuss about the DC machine, its construction, working principle. So now in this lecture, we will study the classification of the DC machine, separately excited DC machine, what is it and how it is worked. Next, we will move on the self-excited DC machine, its circuit diagram. After this, we will move on what is the armature winding and the type of armature winding used in DC machine. Next, we will move on the EMF equations, electromotive force equation. So we can prove this equation. So this is the content of our presentation or lecture 2. So let's start with topic 1, the classification and type of DC machine. The excitation of the DC machine. The DC generator converts the mechanical power into electrical power. The magnetic flux in a DC machine is produced by the field coil carrying current. The circulating current in the field winding produce a magnetic flux, and the phenomenon is known as the excitation. So this is all about the excitation. DC machine, DC generator or DC motor are the single excited machine. Means we supply one side of the machine. So the DC generator is classified according to the method of their excitation. DC machine are classified according to the type of excitation. Number 1 is a self-excited DC machine, and number 2 is a separately excited DC machine. Actually, in a previous class, we will discuss about what is the machine, motor and generator. If we write the machine, means we consider both the cases like motor as well as generator. So DC motor is also classified into two categories, self-excited DC motor and separately excited DC motor. Similarly, in case of generator, it is also classified into two categories, self-excited or self-bound DC generator, separately excited or separately bound DC generator. In a separately excited, if we say that the machine, so we consider both the cases like motor as well as the generator. In a separately excited, there is no classification, but in a self-excited machine, further classified into three categories: series DC machine, shunt DC machine and compound DC machine. And compound further classified into two categories, long shunt compound and short shunt compound. So this is all about the types of the DC machine according to their excitation. We will move on next topic, separately excited DC machine. A DC generator whose field winding or coil is energized by a separate or external DC source is called as a separately excited DC generator. Similarly, in case of the motor, so normally we can say that if machine excited by a separate source or separately is called the separately excited DC machine. The flux produced by the pole depends upon the field current with the unsaturated region of the magnetic material of the poles. That is, flux is directly proportional to the field current. But in the saturation region, the flux remains constant. The figure of self-excited DC generator is shown below. In this diagram, we can see that the field winding and the armature winding. DC machine has two winding. In a previous class, we will discuss the DC machine has two winding. One is called field winding, another is called the armature winding. Field winding is placed on a stator and the armature winding placed on the rotor. So this is a simple diagram for the separately excited DC machine. IF is called the field current, IA is called the armature current, IL is called the load current, and V is called the output voltage. EB is called the induced EMF or back EMF or generated EMF, and RA is known as armature resistance. Separately excited DC machine, the IA is equal to IL, where IA is the armature current and IL is the line current. The terminal voltage is given as V is equal to EG minus of IA into RA, where V is called the terminal voltage, EG is called the generated EMF or generated voltage, IA is called the armature current, and RA is called the armature resistance. If the contact brush drop is known, then the equation number 1 is written as V is equal to EG minus of IA RA minus of 2 VV. VV is called the brush voltage. The power developed is given by the equation so below. The power developed is equal to EG into IA. We can know that the simple formula P is equal to VI. So the output power is equal to V into IL or is equal to V into IA. So this is the equation number 4 is called the power output in a separately excited DC machine. Now the next topic is a self-excited DC machine. Self-excited DC generator is a device in which the current to the field winding is supplied by the generator itself. Because the current supplied by the machine itself, so it is known as the self-excited DC machine or DC generator or DC motor. In a self-excited DC generator, the field coil at P connected in parallel with the armature in the series, or it may connected partly in series and partly in parallel with the armature winding. The self-excited DC generator is further classified as, or we can say that the self-excited DC motor or the self-excited DC machine is further classified into 3 categories. In a previous slide, we can see the classification diagram. So number 1 is a series bound generator, second is a shunt bound generator, and third is called compound bound generator. Or we can say that series motor, shunt motor, and compound motor. And compound are further classified into 2 categories, long shunt compound and short shunt compound. So next is a shunt bound generator or shunt motor or shunt machine. In a shunt bound generator, we consider these 3 terms because the machine is known as the motor or machine is also known as the generator, depend on the energy conversion state. If convert electrical energy into mechanical energy, so called the motor. If convert mechanical energy into electrical energy, so called as generator. So we study about the shunt bound generator. In a shunt bound generator, the field winding is connected across the armature winding, forming a parallel or shunt circuit. We can simply say that if the field winding is connected parallel with the armature winding, so this arrangement is known as the shunt generator. Therefore, full terminal voltage is applied across it. A very small field current ISH flow through it because this winding has many turns of fine wire having very high resistance RSH. You can see the diagram. The field winding resistance RSH, ISH is called the shunt field current, IA is called the armature current, IL is called the load current, EB is called the back EMF, and RA is called the armature resistance. The shunt field current is given as ISH is equal to V upon RSH. We can find this current with the help of Ohm's law. V is equal to IR. So I is equal to V upon R. So we can write ISH is equal to V upon RSH, where RSH is the shunt field winding resistance. The current field ISH is practically constant at all load. Therefore, the DC shunt machine is considered to be a constant flux machine. Armature current is given as the equation IA is equal to IL plus ISH, where IA is called the armature current, IL is called the load current, and ISH is called shunt current or shunt winding current. So the terminal voltage is given by the equation V is equal to Eg minus of Ia into Ra, where V is called the terminal voltage, Eg is called generated voltage, Ia and Ra is called the armature current and armature resistance. So next we will move on series bound generator. A series bound generator, the field coil are connected in series with the armature winding. The series field winding carries the armature current, and the series field winding consists of few turn of wire, of thick wire of larger cross-sectional area and having the low resistance, usually of the order of less than 1 ohm, because the armature current has a very large value. So in a series machine or series motor or series generator, the simple we can define if the series winding is connected or if the field winding is connected series with the armature winding, so the machine is known as series machine or series DC machine. Its conventional diagram is so below. We can see the diagram. In this diagram, the field winding is connected series with the armature winding. So this machine is known as series bound generator. Now the series field current is given as ISE. We can denote the series current ISE is equal to IL is equal to IA. RSE is known as the series field winding resistance. The terminal voltage is given as V is equal to Eg minus of Ia into Ra minus of ISE into RSE, where V is equal to voltage, Eg is called the generator voltage, Ia and Ra is called the armature current and armature resistance, ISE and RSE is called the series field current and the resistance of the series winding or field winding. So V is equal to Eg minus of I in bracket Ra plus RSE. If the brush contact drop is included, so the terminal voltage equation is written as V is equal to Eg minus of Ia in bracket Ra plus RSE minus of 2VB. Finally, the power developed in a series bound generator is equal to Eg into Ia. And the power output of series bound generator is equal to V into IL or is equal to V into Ia. The flux developed by the series field winding is directly proportional to the current flowing through it. But it is only true before magnetic saturation. After the saturation, flux becomes constant even if the current flowing through it is increased. So next classification is compound bound generator. Compound bound generator is the combination of series and shunt machine. We can say that in a compound bound generator, there are two field winding. One is connected in series and another is connected in parallel with the armature winding. Compound bound generator are classified into two types. Number one is called the long shunt compound bound generator and number two is short shunt compound bound generator. Now the next topic is armature windings. Armature winding of the DC machine. Basically, armature winding of the DC machine is bound one of the two methods. Number one is a lap binding and number two is a wave winding. The difference between these two is mainly due to the AND connection and the commutator connections of the conductor. To know how armature winding is done, it is essential to know the following terminology. Like pole pitch. What is pole pitch? It is defined as the number of armature slots per pole. For example, if there are 36 conductors and 4 poles, then the pole pitch is 36 by 4 is equal to 9. Next, we know that coil span or coil pitch represented by S is defined. It is the distance between the two sides of a coil measured in terms of armature slot. Next is the front pitch represented by YF. It is the distance in terms of armature conductor between the second conductor of one coil and the first conductor of the next coil. Or it is the distance between two coil sides that are connected to the same commutator segment. Next is back pitch represented by B. The distance by which a coil advances on the back of the armature is called the back pitch of the coil. It is measured in terms of armature conductors. Next is resultant pitch represented by YR. The distance in terms of armature conductor between beginning of one coil and the beginning of the next coil is called as resultant pitch of the coil. The armature winding can be done as a single layer or double layer. It may be simplex, duplex or multiplex. And this multiplicity increase the number of parallel paths. In a diagram, you can see what is back pitch, what is front pitch represented by B and by F, resultant pitch by R, the diagram of lap binding and wave binding. Now the lap binding. In a lap binding, the successive coil overlap each other, so it is called the lap. In a simplex lap binding, the two ends of a coil are connected to adjust commutator segment. The binding may be progressive or retrogressive. A progressive binding in the direction in which the coil is bound. The opposite way is retrogressive. The following image is show the progressive simplex lap binding. Now next is a wave binding. In a wave binding, a conductor under one pole is connected at the back to the conductor which occupy an almost corresponding positions under the next pole which is opposite polarity. In other words, all the coils which carry EMF in the same direction are connected in series. The following diagram show a part of simplex wave binding. The next topic is EMF equation or electromotive force equation. So EMF equations of the DC generator. We consider a DC generator with the following parameters, where P is equal to number of field pole, phi is equal to flux produced per pole in Weber, Z is equal to total number of armature conductors, A is equal to number of parallel path in armature, N is equal to rotational speed of armature in RPM, revolution per minute. Now, the average EMF generated per conductor is given by d phi by dt volt in equation number 1. The flux cut by one conductor in one revolution is equal to d phi is equal to p phi in Weber. The number of revolution per second speed in RPS is equal to n by 60. Therefore, time for one revolution is equal to dt is equal to 60 by n second. From equation number 1, EMF generated per conductor is equal to d phi by dt is equal to p phi n by 60. This is known as the equation number 2. Above equation 2 gives the EMF generated in one conductor of the generator. The conductors are connected in series per parallel path, and the EMF across the generator terminal is equal to the generated EMF across any parallel path. Therefore, generated EMF Eg is equal to P phi n Z by 60 into A. So this is the EMF equations of the generator. It's called Eg, generated EMF. If we consider the motor case, so it is represented by EB. EB is called the back EMF. The formula is same, phi Z and P upon 60 into A. For simplex lap binding, the number of parallel path is equal to the number of poles. That means A is equal to P. Therefore, for the simplex lap bound DC generator, Eg is equal to P phi n Z upon 60 into P, because A is equal to P means number of poles. This formula used for the numerical purpose. For simplex wave winding, the number of parallel path is equal to 2. Means P is equal to 2. So therefore, for simplex wave bound DC generator, Eg is equal to P phi and Z upon 60 into 2 means 120. So these both formula are used for the numerical purpose. The main EMF equations of the DC generator is Eg is equal to P phi and Z upon 60 into A. So this is called the EMF equation of the generator. Now this is a reference. Thank you for watching the video.